Okay, so today I want to talk about Flowtune in a few minutes. This is joint work with Hari Balakrishnan and Devraj Shah from MIT. So what is Flowtune? We tried to create an architecture for data center networks where we can allocate network resources with extremely fast convergence time to the optimal allocation, where we have a very explicit notion of what the optimal allocation is, and a system that has a very flexible deployment story. So basically, in software only. So we start with kind of a very similar motivation to Lavanya's talk, the previous talk, where we looked at these existing schemes. We looked at, just to drop some names, DCTCP, pFabric, CODL with SFQ, XCP, and others. Lavanya showed RCP, but similar. We saw similar results. And we think the problem is that these schemes are packet-centric. So what I mean by that is these schemes specify what to do with the switches per packet. So how do you queue packets? For example, drop tail, stochastic fair queuing, priorities, and how do you mark or modify packets? And at the end hosts, these schemes specify when the next packet should be sent and how to react to these per packet congestion signals. And this has the disadvantage, like three major disadvantages. So first, in the data center, we mostly care about per flow objectives. And translating those into per packet mechanisms is hard, and sometimes we don't get it right in every situation. A second issue is these schemes take several round-trip times to converge, and Lavanya mentioned that in the previous talk. And lastly, if you want to change the policy, frequently you have to change switch algorithms, which we all know is very painful to get into hardware, and many times the server algorithms, which is hard to do as well. So we tried to overcome these. So what we do with Flowtune, we take a somewhat different approach, and if you take just one thing out of this talk is this, I think, is that maybe as a community we shouldn't allocate resources on a per packet basis with per packet mechanisms, but rather allocate them per flowlet. And here we have a specific definition of flowlet. Here we mean a batch of packets that are queued at a sender. So if the application wants to send a 1 megabyte buffer, all of the packets for this 1 megabyte buffer are the same flowlet. And we argue, like we heard previously today, that allocations should only change when the set of flowlets alive in the network should change. So for example, if you have this network with these two flows, you either want to prioritize one over the other, or you want to allocate resources 50-50, or 10%, 90%. But this should remain constant as the flowlets, as the set of flowlets remains constant. And the time you want to change allocations, usually with these per flow objectives, is when flowlets arrive and when flowlets terminate. A second part of our approach, which is a design choice, is we want to centralize the allocation. So here I'm arguing for the Oracle approach, and we think that the Oracle is feasible in quite large network, in medium-sized networks. I'll show some results later. And here we wanted to overcome the multiple RTTs that it takes to converge. So let me run through an example. Let's say A has a flowlet for B. A opens a TCP connection, starts transmitting, and in parallel, it tells the allocator here, this process Hadoop on A has some packets for B. The allocator looks at this flowlet and assigns rate. It tells A, here you can blast at line rate. So at the time that A gets this allocation from the allocator, it can just blast away at line rate. So very quickly opens the window. Now another flow enters the network. C has some packets for B, and C opens its connection and in parallel contacts the allocator, tells it, I have some data from this ads service for B. The allocator looks at these flows again and says, ads is more important in our network than Hadoop. So I'm going to allocate 1 gigabit to A and 9 gigabits to B, tells the endpoints the rates, and the endpoints enforce this. So you might say, hey, this doesn't seem like a hard problem. You phrased it this way. You just, allocate rate. You have a set of flowlets live in the network. Just assign the rates. Well, this is actually harder than it seems. So even if you have an optimal allocation, now you're trying to add a flowlet. The problem is that the updates to rates cascade in the network, making the whole approach very expensive. So let me show this example. So look at this link over there. The new flow shares this link with an existing flow. So the rate for the existing flow might need to be lowered to accommodate the new flow. Now, on a few links, there's spare capacity that you would want to allocate to different flows. So the rates of these flows change, and so on and so on. So in general, just an update to a small part of the network, to one part of the network, very quickly cascades across the network, making it really expensive. The second problem is, we don't even know what we're trying to optimize. Are we trying to get just a variant of TCP that converges faster? Are we trying to get the same thing as TCP? Can we get something better? How can we make this more explicit? So to address this, we leveraged the NUM framework, the Network Utility Maximization Framework proposed by Kelly and his co-authors in the late 90s. So I'll show the economic intuition for the NUM framework. So what we do is we assign a price P for every link. And we adjust P based on supply and demand, where supply is the link capacity, and demand is the sum of the rates of all the flows that traverse that link. And we adjust prices, if flows want to send over the link capacity, then the price increases. If flows want to send below the link capacity, price decreases. And now, given prices, each flow can optimize its own rate. So each flow knows its utility. So this is what it gains from each allocation. So what it gets at 1 gigabit, at 2 gigabit, at 3 gigabit, and so on. And it also knows the price it pays per gigabit per second. So it can subtract the two and get its profit. So revenue minus cost equals profit. And each flow can selfishly optimize its rate. So it's going to choose the point where it gets the most profit, the rate where it gets the most profit. So here it would choose 2.2 gigabits per second. And the magic of NUM is each flow optimizes its own profit selfishly, but the prices drive the entire system to a global optimum. So maximizes the sum of utility from all the flows. And the secret sauce in any such NUM framework-based scheme is how to exactly update the prices. Right? There's supply and demand. How do you change the prices? What is the delta when you have a difference in supply from demand? And we have some innovation there, but I don't have time to explain it. But I'm happy to talk about it offline. So this is an iterative scheme. So you adjust prices based on rates, then rates based on prices based on rates based on prices. You need several iterations for a system to converge. And usually, we've found that it takes around 100 iterations to converge. Unfortunately, this is way too slow to run in practice. We wanted something much, much faster. So, our first attempt at trying to solve this is saying, let's run one iteration. So we update the network state, run one iteration, then maybe some other flow, let's arrive or leave, run another iteration. So update, run another iteration. The problem is that this doesn't behave very well. So what happens is that links are over-allocated. So let's say a new flowlet arrives in the system. There's extra demand on some links. But the prices for these links should increase. But for a few iterations, the prices are too low. And flowlets oversend on these links. So this causes congestion, buffering, packet drops that we want to avoid. So what we did with Flowtune is we introduced another step, a normalization step, after the optimization iteration. So what this does is for every link that is over-allocated, it scales down its flows that traverse that link so that the link is not over-allocated anymore. And what this gets is, if you look at the top line, we're able to get 99.7% of the optimal throughput while completely avoiding these over-allocations like packet loss, buffering, and so on. So just to review what the architecture looks like, endpoints send these notifications of flowlet arrival and termination to the allocator. The optimizer continuously runs these iterations of NUM. and kind of updates its flow state, runs an iteration, updates flow state, runs an iteration. And after every iteration, it copies the rates to the normalizer, which normalizes the rates and sends updates to the endpoints. So I have, yeah?
So the iterations are taking place quickly, though. They're just happening in computation. There's no round trips for the prices to be
exactly. You don't need to propagate kind of.
in the controller.
Yes, everything runs on the same kind of CPU on the controller. Yeah, so a couple of results. So we ran this experiment to find out how quickly Flowtune converges to the right allocation in a network. So what we did is a similar experiment was run in the DCTCP paper. So what we did is we had 5 senders and 1 receiver. And every 10 milliseconds, we started a new sender sending to the receiver. And then after 5 senders started up, after every 10 milliseconds, we stopped one of the senders. So what you would want to see is what is in the second graph, what Flowtune achieves, that with n senders, each flow gets, so what this is a function of time, so x is time, y is the rate for each flow. So there should be 5 lines there on every graph. So in Flowtune, all the lines are overlap. And when there are n senders, every sender gets exactly 1 over n of the network, of the link capacity. What you can see is DCTCP kind of oscillates around the fair allocation. pFabric minimizes flow completion time, so it just chooses the one flow and goes with it until it finishes. Caudal with SFQ has a lot of packet drops, so the rates that the applications see are very bursty. And XCP is very slow to hand out traffic because it needs to measure the network. It takes a long time for it to react. We've been able to scale Flowtune. You can see the last line of the graph there. With 64 cores, we can allocate 4,600 servers, 49,000 flows in 31 microseconds. So it's around 2 to 3 round trip times. So your network can allocate resources very quickly. So I've talked a bit about Flowtune. We've used kind of Flowlet-based control and used the num framework with a normalization step to get these 3 goals, very quickly converge to the optimal allocation, have an explicit kind of notion of what is optimal, and do this entirely in software. And even if you disagree with the design decisions, obviously this doesn't scale to the world's largest data centers. But if you think these are exciting goals to have, then please come talk to me later and we can do something together. So I'm happy to take questions. You can ask about fault tolerance, about
What did he ask?
about, yeah.
I'm just curious, maybe you have a feel for this, or maybe somebody else does, but in your example where you had 4,600 servers and 47,000 flowlets, is that a high or low number of flowlets? Like, would a normal server have thousands, though, simultaneously? Or you've got 10 there.
Right.
And I just don't have a gut feel for that. And of course, it depends on the application.
So I think the VL2 paper published results at Microsoft from, they're pretty kind of old by now. It's 2010, I think. So they had this distribution of number of flows active per server over very coarse granularity. This you would only account for the actual live flows and not, they took 10 milliseconds or something. And it shows, like, if you look at the distribution, the median is around 10. Or
I'm actually looking for Atul. I thought he's gone on record saying don't use that CDF or anything. So, so actually I had a different question. So I mean, you guys did this FastPass stuff, right? So it seemed like that was, the key difference is you're doing more kinds of utility functions. Is that what it is?
Yeah, so here you have an explicit utility function.
Okay.
that you can have per flow. So you can. So FastPass is a framework where you can prioritize different flows when you allocate, and you can prioritize them differently between time slot to time slot, but it's still a packet-based scheme. It was really hard to express a lot of these in FastPass, hard or sometimes impossible. And also we tried to scale, then we realized that you have this cascading problem in the network, right? We said, if we just scheduled flows instead of packets, we'd do a lot less work. But then we found out that it's not as easy as it seems, but we were still able to scale, 10 times more.
So it's both more expressive and more scalable. Is that what? Okay, cool.
And the nice thing is that in some sense, FastPass, you have to do per packet work. So if you go from 10 gigabit to 40 gigabits to 100 gigabits, you automatically scale down. It hinders your scaling. Whereas here, if you allocate rates, then maybe you're not as sensitive to the technology you're using.
So since you asked for open-ended questions, do you have ideas about how you would make this less centralized? Would you have to worry about things like, I guess either the sort of resources get sharded, or you have some kind of control loop, and then maybe issues like stability.
So first, you said if you have any notion of how to make this less centralized, I'm not sure that is a goal. Centralized, we kind of know as a community how to build centralized systems now. More than before. We have failover, we have quorums that decide on what is the primary replica. We have a lot of tools at our disposal, and Flowtune is not as sensitive to faults as FastPass is. But that said, scaling is an issue. So how do you use multiple computation resources spread across a lot of servers to use the system? And yeah, that is a concern. We have this scheme that I hadn't had time to talk about. It's in the bottom of how to distribute this resource allocation in networks to many cores. And we believe this can generalize to many servers. So many of these allocators working in tandem with this pattern of communication between them that has good properties. We haven't tested it out yet, so it's still an open question whether we can scale up using multiple machines.
So currently when you make change, you will compute everything or just make the incremental compute?
We make an incremental computation. So the optimizer runs one iteration at a time and keeps the rates from the old iteration. So it computes prices based on rates and then rates based on prices and so on. So what we do is we just do one iteration of this, then maybe add some flowlets and remove some flowlets. So the prices are around what they're supposed to be. Then we run another iteration and so on. So yeah, we reuse, we update state.
Do you have a sense of how far off from the utilities you are, because you kind of stop before the thing actually converges?
Yeah. So if you have long-running flows that are more than 100 RTTs or 100 iterations of the algorithm, that part of so you have a new flow, that part of the network is going to be in disruption, so it's not going to converge for a few iterations. Maybe not 100, 5 or 10 iterations. After 10 iterations, you're fine because you've converged. The problem with normalization is you trade off optimality. You just want to kind of cramp all your flows onto the links, just extinguish fires. So for maybe a few few iterations of the algorithms, you're not optimal. But we found that this graph shows that at least in this example, it converges very quickly. Thank you.